So very good morning. So in the last class, I have explained about the derivation of the rectification efficiency and the ripple factor. Okay, it is for the half wave rectifier as well as for it is for the full wave rectifier. Okay, and in this class we are going to see about the sample problems on the rectifiers, and also we'll see the filters concept. So it is as per the block diagram of the regulated power supply has been considered. So what's the first part is the transformer. It is to be followed by the rectifier there. So already you learned about the rectifier now, and it is to be followed by the filter. So that filter concept also it is to be studied in this class. So in this class we are going to study the sample problem on the rectifiers, and we'll see the definition of the filters, and we'll see the need for the filters. We'll see the types of the filters. We'll see the working of the C filters, and also the working of the pipe filter. Okay. So if you take an example problem, so in a center tapped full wave rectifier, so the RMS, the half secondary voltage is equal to 10 is equal to 10 volts, assuming the ideal diodes and the load resistance of RL is equal to 2 kilo ohm, and is asking to find the peak current, okay, DC load voltage, okay, ripple factor, and the efficiency of the rectification. Okay, understand the questions and identify the given values first. So as per this one, in the center tap, okay, full wave rectifier, so the RMS half secondary voltage. So the RMS voltage is equal to, it is 10 volts. So it is Vs. S is the secondary voltage of the transformer. It is Vrms is equal to 10 volts. Okay, it is for the full wave rectifier with the center tap. And he is asking, and he is also mentioning, assuming the ideal diodes. Ideal diode means the internal resistance of the diode is assumed to be the zero, and also if you take the series resistance, it is also to be the zero. So this RF is equal to 0 ohm and RS is equal to 0 ohms, and the load resistance of RL is equal to 2 kilo ohm. So RL is equal to 2 kilo ohm. So he's asking to find the peak current. What is the peak current? This is the maximum current. So it is to find the IM. It is the peak current. And is also asking to find the DC load voltage. So VL. So it is across the load. So it is VL. Okay, DC is to be calculated. And he is also asking to calculate the ripple factor. It is ripple factor is to be calculated, which is equal to R. And he also asking to calculate the efficiency of the rectifications. Eta is to be calculated. So all these four parameters is to be calculated. Okay. I am going to repeat once again. So it is because understanding the question is very important. In the center tap of the full wave rectifier, the RMS secondary voltage is equal to 10 volts, means it is Vrms is equal to 10 volts. Assuming the ideal diodes means the internal resistance, it is RF and RS is equal to 0 ohms. If you take the load resistance means RL is equal to, it has been given as the 2 kilo ohm. He is asking to find the peak current, it is IM is to be calculated, asking to calculate the DC voltage. So the VLDC is to be calculated, and is asking to calculate the ripple factor and the efficiency. Okay, and we'll find the peak current first. It is, what is the formula for the peak current? This is Im is equal to, it is Vm divided by Rs plus Rf plus Rl is there. So all these formulas is already listed in the previous class. I think you know about that one. Okay, so for that purpose, so this, what is the value of the Im? Im is equal to, it is Vm divided by Rs plus Rf plus Rl. And what is the value of the Vm? Vm is equal to, it is Vs RMS into root 2. Okay, it is a root 2 into, it is Vs RMS. So in place of the Vm, I'm going to place as the root 2, it is Vs RMS divided by Rs plus Rf plus Rl. And all these values is to be placed in this equation. So this Vs RMS is equal to 10 is there. So it is equal to root 2 into 10. Rs and Rf is equal to 0, 0 is there. So it is equal to 0 plus 0, and RL is equal to 2 kilo ohm. ohm is there, it is 2 into 10 to the power of 3. So K is equal to 10 to the power of 3, 2 into 10 to the power of 3. So if it has been simplified with the calculator, okay, so that you can able to get this is equal to 7.07 milliamps. Okay, and after that, if you want to calculate the DC load voltage, I think you have understood this one. Okay, so this RS is given, RF is there, RL is also given, so it has to be placed in this equation. And this VM, it's again one more formula. It is root 2 into it is VS RMS. So this VS RMS is given, and all these values is to be placed and it is to be simplified. You can able to get the IM. In the same way, in order to get the DC load voltage, it is a DC load voltage with the ideal diode. It is VL DC is equal to 2 Vm by pi. It is also explained in the previous class. If you take for the full wave rectifier, this is equal to 2 Vm by pi. If you take for the half wave rectifier, this is equal to it is Vm divided by pi. Okay. So which is equal to it is 2 into it is root 2 into 10 divided by pi. It is once again the root 2. It is because what's the value given is equal to Vm. It is what's the given value is for the Vrms. So this Vm is equal to it is root 2 into it is Vrms is there. So 2 into it is root 2 into it is Vrms. So it is equal to 2 into root 2 into 10 divided by pi, which is equal to 9 volts here. Okay. And in order to calculate the ripple factor, it is for the full wave rectifier. So what's the formula for the ripple factor? It is VLRMS. Initially, I'm going to calculate the AC load, and after that you can calculate the ripple factor. It is VLRMS is equal to ILRMS into RL is there. So which is equal to IM divided by root 2 into RL. So I'm going to place the value of the IM. So it has been calculated here. So IM is equal to 7.07 has been calculated. If it is placed in this equation, IM is equal to 7.07 divided by root 2 into 2, so that you can able to get it as the 10 volts after simplification. So if you want to calculate the ripple factor, R is equal to it is VL RMS whole square minus VLDC whole square divided by VLDC, and it is to be under root here. So it is what is the value of the VLRMS? So it has been calculated as of the 10 volts. What's the value of the VLDC? So it has been calculated here. VLDC is equal to 9 volts. So it is to be placed in this equation. VLRMS is equal to 10 volts. So it is 10 square. VLDC has been calculated as the 9. It is 9 square. It is whole to the power of 1 by 2 means it is under root 2 whole divided by 9. So that you are going to get after simplification it is equal to 0.483. If it is multiplied with the 100, so that you can able to get in terms of the percentage, which is equal to it is 48.43%. And and efficiency formula, efficiency is equal to 8 RL divided by it is pi square into RS plus RF plus RL. Already you know that RS and RF is equal to 0. So this eta is equal to 8 divided by pi square. Okay. So this RL and is the RS equal to 0, RF equal to 0 has been placed, and RL is going to cancel 8 divided by pi square, which is equal to 0.8105, which is equal to 81.05%. Understood? So in this way, okay, according to the formula, so that you can able to calculate the required values. Okay. And I think you have understood here. It is based on this one. So it is what this problem is to be considered for the center tap full wave rectifier. In the same way, if we ask it for the bridge rectifier also, all these parameters is going to remain the same only. So it is because whatever the formula, either it can be the center tap or it can be the bridge rectifier, all the formulas is going to remain the same thing here. And if it is asked for the half wave rectifier, according to that it is to be get changed here. Okay, so that you can make use of the correct formula, and in this you can able to calculate here. And the next one, if you take as okay, and the next we'll move on to it is filters here. Okay, it is what is the I said that if you take the block diagram of the RPS is to be implemented by what here? First is having the input from the AC mains, is to be inputted for the rectifier. I'm sorry, inputted for the transformer. Output of the transformer is inputted into the rectifier. The output of the rectifier is to be inputted into the filter. Okay, and of that filter circuit. Okay, so we'll see now. What's the meaning of the filter? Its definition is available in the name itself. A filter is used to remove the unwanted part. Okay, a filter is an electronic circuit. It is used to remove the unwanted part of the signal. Okay, and it is what is the need for the filters in the power supply. It is why you should make use of the filter in the power supply. So a filter circuit is used to remove the AC component in the rectifier. So already you know what's the definition of the rectifier. A rectifier is the one which is used to convert an AC voltage into the pulsating DC. What is that pulsating DC? It is consisting of the DC component as well as an AC component, but as per our requirement, so only the DC is to be required. So in order to remove that AC component, so you are going to use the filters. Yeah, so a filter is needed. It is to eliminate the ripples and to allow only the DC to pass towards the load and to block the AC and to smoothen the signal and produce a pure DC. This is the actual requirement or the actual operation of the filter. Okay, I'm going to repeat here. So a filter is an electronic circuit. It is used to remove the unwanted part of the signal. So a filter is used to remove the AC component present at the output of the rectifier. At the output of the rectifier, it is having an AC as well as the small amount of the AC as well as the DC. So for that purpose, it is called as the pulsating DC. In order to remove the ripples, so a filter is to be required here. So a filter is needed to eliminate the ripples, to allow only the DC to pass towards the load and to block the AC and to smoothen the signal and produce a pure DC. Okay, this is the need for the filters in the power supply. If you take the types of the filters, so according to the components uses, so the filters is to be mainly classified into the four types. It is one is an inductor filter, which is also it is called as the L filter. Another one is the capacitor filter, is called as the C filter. One more is the LC filter. It makes use of an inductor as well as the capacitor. One more is the pi filter. It is also called as the CLC filter. Okay, if you take the types of the filter, it is to be classified into the main four types: inductor filter, okay, capacitor filter, LC filter, and CLC filter. If you take the basic working of the capacitor and the inductor, a capacitor allows only AC to pass through it and it is going to block the DC. Inductor operation is opposite to the capacitor. An inductor allows only the DC to pass and it is going to block the AC. These are the important, it is working of the capacitor and inductor to be remembered. Okay, and according to the syllabus, it's having only the working of the capacitor filter and the working of the pi filter here. Okay, so a capacitor allows only AC to pass and an inductor allows only the DC to pass. Okay, so initially we'll see the working of the capacitor filter. So this is the circuit diagram of the capacitor filter. The input for the capacitor filter is the pulsating DC. What is this pulsating DC? It's nothing but the output of the rectifier. Okay, so it is having the rectifier circuit here. So that output of the rectifier is inputted for the filter. If you take the filter means it's nothing but only a single capacitor. It is to be connected across. It is to be connected across means it is to be connected in parallel. It is to the load resistance RL across the load here, and its output it is going to get it as in this way. This period is called as the charging, and it is to be called as the discharging. So increasing the voltage slightly is called as the charging. If it is decreasing, the period is called as the discharging period. Okay. So, what the property of the capacitor? It allows AC component and it blocks the DC component. Okay, no. So, for that purpose, if you apply the pulsating DC signal, it is for the filter. It is going to be appear at this point. So, as the capacitor, it will allow only AC. So, the AC signal it will flow into the capacitor, and after that it will flow into the ground here. But at this point it's remaining only the DC, and it is going to be appear across the load here, so in the load, so that you can able to get the DC signal here. Understood? It's very easy. Okay. So AC, it will pass into the ground, and only the DC, it will flow towards the load resistance RL. So if you apply the pulsating DC signal, okay, it is going to flow into the upper line here, and the capacitor, it will allow AC to pass into it, so it is going to block the DC, and it will allow to pass AC into the ground here. And after passing the AC into the ground, at this point it is going to be consisting of the blocked DC, and it will flow at the this load resistance RL. And if you take the output across the RL, so that you are going to get the DC signal, so the AC has been removed. So a signal in terms of the full wave rectified output is to be obtained as in this way. It is called as the smoothened signal. And if you take its working, okay, it is to be dependent on the diode also here. So it is called, from at this point to at this point, it is called as the cut-in point. It is the charging period. And from at this point to at this point, it is called as the cutout point, the maximum peak at which it reaches. This is the discharging period. Okay, you can able to see the exact time of the T2, from upper peak to it is lower peak is the discharging period. And if you take from the lower peak to the maximum peak is the T1, it is charging period. What this lower point is called as the cut-in, and if you take the upper point is called as the cutout here. Okay, and if this is going to be combined, it is going to indicate the T by 2 cycle. It is an half cycle here, and it is to be repeated for the succeeding cycles here. So it is during the positive half cycle, so the capacitor is going to charge up to the peak value of the transformer secondary voltage Vm. So it is going to charge up to the peak value in it is under the positive half cycle, and the Vm, it will try to maintain this value as the full wave input drops to 0. It is going to try to maintain this voltage only until it reaches the 0 here. And what this capacitor is going to discharge, it is through the RL, this is slowly until the transformer secondary voltage again increase to the value greater than the capacitor voltage. It will be keep on decreasing until the another cycle is going to be initiated here, and its value should be greater than the capacitor voltage. And what the diode is going to conduct for a field which depends on the capacitor voltage here. So this is about the what the capacitor filter. The important point to be remember in this case is what this capacitor is. It will allow AC to pass, so for that purpose it is to be connected in parallel to the load. So it is when you apply the pulsating DC, it will pass the AC into the ground, and in the output you can able to get only the DC. Our intention in this case is to eliminate the AC. So the AC has been eliminated, and output you can able to get only the DC. This is about the capacitor filter. If you take the CLC filter or the pipe filter, in the CLC filter, what happens here? Okay, so it's nothing but CLC. It is capacitor, inductor, capacitor. So it is capacitor is to be connected in parallel, assuming this as the C1, and the inductor is to be connected in series, and again the another capacitor is to be connected in parallel to the load here. And the arrangement is going to visible as the symbolic representation of the pipe. The upper line is acting as an inductor, what this vertical lines is acting as the capacitor, so it is also called as of the pipe filter here. Okay, so all these three components are arranged in the shape of the Greek letter pipe. So for that purpose, it is called as of the CLC filter. Okay, in this case again the same. I think you so I explained what this capacitor it will do. It will allow the AC to pass, and it is what about the inductor? Inductor will allow only the DC to pass. It will block the AC here. So if you apply the pulsating input for this circuit, so initially the capacitor 1, it will allow to take the AC component into it, and it is flowed into the ground. And at this point it is having only the DC. Unexpectedly, if it is having any of the AC component at this place, means this inductor is going to block that AC component, and it will allow to pass into it only the DC. And at this point again, if any of the AC is available, it is allowed to flow into the ground, and at the output it is going to take only the DC. It's nothing but the filtering. In this case, it is to be filtered at the one level, it is to be filtered at the second level, it is to be filtered at the third level. So the signal is a refined three filters. Okay, the signal is to be get refined with the three layers here. It is filter 1, filter 2, filter 3. So it is itself is called as of the CLC filter. So the input capacitor C1 is selected to offer the very low reactance to ripple frequency, hence the major parts of the filtering is done by the C1. C1 means you can see this is the C1. Okay, so the major of the filtering is to be done is to be so the measure of the filtering is to be done by this capacitor only. It consists of the one inductor and the two capacitors here. So in the it is most of the remaining ripples are removed by it is combining the action of the L and the C2. So it is most of this action is to be taken by this also in this case. So if you apply the pulsating DC, so the AC is to be flowed into the ground by the first capacitor, and if any of the AC is available, it is to be blocked by the inductor, and only it is going to take the DC in this case. And unexpectedly, if any of the AC component has been arrived, means it will flow into the ground with the help of the capacitor C2, and at the output it is going to take only the DC. It is the output, exactly only the DC output here. So it is also to be represented same forms here. What this the half wave patterns, it is nothing but the output of the full wave rectifier. And what about this upper part, it is going to acting as of what the output in terms of the DC. Okay, so this is about the CLC filter here. Okay, so in this class we have studied about what here. So a sample problem so has been solved on the rectifier. Okay, and what the definition of the filter has been studied, and what the need for the filter is studied, and how many types of the filters are available has been studied. And according to the syllabus, it is a C filter has been explained, and CLC filter is also studied. Okay, if you take the sample descriptive questions onto the today's classes, he may ask you to define filter and explain the need for the filter in the power supply. Okay, or he may ask you to list the types of the filter. It is of the four types. Or he may ask you to describe the working of the C filter, it is capacitor filter, or he may ask you to describe the working of the pipe filter. Okay, it is all about the today's class. Okay, in the next class, okay, so that we are going to see about the regulators. Okay, okay. Okay, thank you very much.